Alright, good morning. So we're going to keep going with our oscillation stuff today. I've got three problems that kind of combine oscillations with different stuff that we've learned throughout the year. So conservation of momentum, um, friction on two blocks, and then instead of one spring, what happens if we've got two springs? So it should be a little bit more interesting than last time. We've got all of our spring-based equations from our formula sheet over on the left. Okay, starting out with this one that I had you skip from last time. So we are firing a bullet horizontally into a block of a mass m, which is initially at rest but at the end of an ideal spring on a frictionless table. The moment the bullet hits, the spring is at its length L. The bullet becomes embedded in the block, and simple harmonic motion results. Okay, so I'm going to call this, it's a little bit hard to see, but I'm going to call this mass 1. So I've got a mass 1 and a mass 2. Okay, so starting out with conservation of momentum. Oop. Guess I can't zoom in. So with my conservation of momentum, I had mass velocity for the bullet. And then when I hit the block, I'll have both masses together with their final velocity.
Yep.
So my final velocity at the moment this hits the block is going to be mv divided by m2 plus m1. Okay, if I wanted to know what the amplitude was, then I can use energy to figure out where this would have stopped. So I'm going to push the block somewhere in here until all of the kinetic energy has become potential energy. Okay, so all of the kinetic energy I would have had initially has to become potential energy at the end by the time I hit the amplitude, which will be a displacement of my amplitude. So I've got that x sub a. So this is 1/2 of mv squared. Our v is the same v that we had last time. Our m is m1 plus m2 because that the moment the bullet hits the block, they're both together.
Yep.
Okay, then we got potential energy. So that's 1/2 k displacement squared. Displacement is my amplitude, and we solve for amplitude. Any questions so far?
Nope.
Okay. Okay, a little bit harder if I wanted to calculate the frequency. So I've got my period for the spring. If I throw that over 1, so that'll be 1 over 2 pi to get my frequency. Oops. Hold on a second. I think I may have just botched this. What should this be?
Oh, m and small m.
M and small m, okay, but they're in the wrong position, so what should change? What's the relationship between frequency and a period?
That's inverse.
Inverse.
Oh wait, so it should be switched up and down.
Right. Okay, let me break out of this really quick. So this one should be I'm looking ahead and I did that right when I substituted it in, but I didn't write it right for that line. Okay, so we got our inverse. Then this might be new, but our angular velocity I could get with radians over time, right? So if I know how many radians are in one rotation, and I know one rotation is over this much time, then I would be able to cancel out my rotations and get radian per time, right?
Mm-hmm.
which would be the angular velocity. So this is 2 pi. I have 2 pi radians in one rotation. And then my frequency is one rotation over my period, right?
Mm-hmm.
So 2 pi f is my angular velocity. So new equation. Um, then our old equation for displacement. So I've got our displacement right now, amplitude. This is angular velocity, time, and our phase shift. We have no phase shift because we started at the equilibrium point. So that means we can substitute in directly. My omega is 2 pi f, so here's 2 pi f instead of omega for t, and everything else stays the same. Okay, so our amplitude, we had solved in the previous problem as our maximum displacement, so I'm just going to sub in what we got for the previous problem. And then I've got my sine where this would be 2 pi times f, my 2 pi and my 1 over 2 pi will cancel, leaving me with just the root k over m1 plus m2.
Mm-hmm.
Okay, any questions on that one?
No, but it looks so complicated.
I don't think it's that bad if we break it apart step by step, right?
Yeah.
Okay. I'll jump over this next one. Okay, so I've got 2 blocks this time. We're on a horizontal frictionless surface, as shown below. We have a coefficient of static friction, which is 0.4, and I want to calculate the max possible amplitude of the spring harmonic motion if there is no slipping. So what I've been given is my coefficient of friction is 0.4. I have a small mass, which is 1 kilogram, and a large mass, which is 10 kilograms. Oops. Once again, mistype, but the calculation's right. So, okay. So I'm going to start out by saying if there is no slipping, then both of these masses are going to be together, right?
Mm-hmm.
So that means the acceleration that's happening on my larger mass should be the same as my acceleration happening on the smaller mass.
Yep.
Therefore, I can look at my acceleration of the larger mass first, which would be centripetal acceleration, which is v squared over r, or omega squared r. Omega is vr, right?
Mm-hmm.
So if we substitute, these should still be equal. So I've got my radius right now is how far we have displaced.
Mm-hmm. Radius? Wait.
The motion of the spring is analogous to our motion of a circle, right? Because
Yeah.
our periodic motion is constantly moving. So if I had a circle, we could model that with a sine function, right?
Mm-hmm.
So the acceleration that's pulling me back to center point, that's pulling me back to equilibrium, can also be thought of as centripetal acceleration. But that means my radius, my distance to the center point, is going to be my displacement from equilibrium.
Mm-hmm.
Okay. So that gives me my acceleration for the large mass is going to be omega squared x. Then my force is mass times acceleration, and my force is also Hooke's law because we are an ideal spring in simple harmonic motion. So I could say, since my force here for Hooke's law, that negative just says I'm moving back towards equilibrium, and this force is also moving towards equilibrium, and my signs are actually the same when I go back to substitute here, but I've got Hooke's law which I'm going to keep positive just to match my other force.
Mm-hmm.
And then my masses, m plus m, and our acceleration that we just found here.
Yep.
Okay, then we can substitute. So this is actually a step we solved for in the previous problem, but my... Oh, sorry, not there yet. One line up. I'm going to solve for w squared. So I'm going to divide by m plus m and divide by x. My x's cancel, and I'm left with k over m plus m. Okay, so then my force is mass times acceleration for my force of friction. My force of friction is mu force normal. So
Mm-hmm.
that's mu mg. My m's will cancel, so my acceleration for the smaller mass is just mu g.
Yep.
Because my acceleration of the smaller mass is the same as my acceleration of the smaller mass that we have up here. We can resub, so mg is equal to just lost my place, hold on.
Mr. Brandon.
Yes.
So wait.
I got it, okay. What's your question?
So math homework is doing all the FRQ in here.
Right, so you've got 4 FRQs for the math homework?
4?
I think so.
The file that you sent?
Right, there's a packet on WeChat.
There are 3.
Oh, okay. Then just do those 3.
Mm-hmm. So when do we go back to school?
We don't know for sure yet, so we've been told we're out for at least until February.
Until the end of February?
Right.
Oh.
If they need to keep us out longer, they'll tell us.
Oh.
Alright, so our acceleration is omega squared x, so that means I should have... Okay, omega squared, which is k plus m over m. K plus m plus m. Okay, there we go. So k over m plus m times x gave me this part. Okay, so then I solve for x, divide both sides, so that'll multiply by m plus m divided by k, and I've got my displacement. And we can substitute in and get our maximum possible displacement, which would be our amplitude.
Mm-hmm.
Okay, any questions on this one?
Maybe no.
Okay, I'm gonna check this last step, so that was the part that kind of got me confused, but this is my acceleration that we found was mu g. My acceleration for the larger mass is the same as my smaller mass, was w squared x. W squared was k over m plus m, so I can substitute. This is w squared x. And I've got acceleration equals acceleration. At that point, we just solve for x and plug in.
Mm-hmm.
Okay. And the last one. So we've got 2 identical springs that are attached to a block of mass m. I want to show that the frequency is 1 over 2 pi root 2k over m. So I'm going to call the center point x for equilibrium. And I'm going to subscript xa for amplitude.
Mm-hmm.
So I'm going to have 2 forces of the spring. They're both going to be Hooke's law. So k displacement, k displacement. But my displacement's going to be different from one spring than the other, right? My displacement for this one would be x plus xa. And my displacement for this one would be x minus xa. Oops, I wrote that wrong. 1 second. This is xa, this is x. Okay, so x minus xa would be this part. Is my displacement for the second spring. Okay, so I've got two forces. They're both going to be acting in opposition to each other, so my signs should be different. So the sum of my forces is negative F1 plus F2. That negative F1 will change my sign in here. So this will become positive xa minus x, positive xa minus x. And I can factor out my k's from both of them because I'm adding. So my negative x and my x will cancel, and I'm left with 2xa. My force is mass times acceleration, so we can substitute 2kxa is equal to my mass times my acceleration, which we said was our displacement times omega squared, which again is our centripetal force. V squared over r is equal to omega squared r. Okay, omega is 2 pi f. That one is our radians per rotation times our rotation per time. We'll allow our rotations to cancel, so that would give me radians per time, which is an angular velocity. Okay, so if I make that substitution, 2 pi f for omega, I'll end up with this, and then we can solve for our frequency. So divide by our mass, divide by xa, which cancels, take the square root of both sides, and then divide by 2 pi, and we get our frequency, which matches what we were trying to prove.
Wait, may I go to bathroom?
So we're actually finished here, so do you have any questions?
No.
Okay, so I'm gonna, your homework is up on Skype and course sites, but you only need to do 1 through 6 on that packet, and we're going to come back and do a couple more next time. So your homework is number 1 through 6.
Number 1 to 6, okay.
Okay, thank you very much.